Hey everyone, this is Joe from graybenchelec. Welcome back to the bench. So a couple weeks ago, I did a video that was going over the different parts I got in an electronics lot I had bought from a local builder. As I was going through it, there's a bunch of parts. One of them that stood out to me was this one here, the T3416 from Teledyne. I believe I pointed these out because I love the Teledyne logo. It's sort of like a geometric flower cut in half. I've had other Teledyne parts, including like germaniums and different ICs and stuff, and it's always just stood out to me as a cool logo. But the number also reminded me of something, but I couldn't pin it down. And then I recalled what it actually was, which was the Reeves Electro ZO, which is their modified Zonk II or Zonk machine Mark II. They use 2N3416 transistors for their pedal here. And so that sort of prompted this video. Actually, it's going to be like a two-part video of me going over that Reeves Electro modified circuit. We'll talk a bit about the original Mark II Zonk machine, and then I have it mocked up on the breadboard, so we'll play and have a listen to that. We'll mess around with some components. We'll look at some of the changes. It appears Reeves makes two versions of the ZO or the ZO, and we'll talk about what I've seen differences between those two versions, at least two versions. We'll also play with some transistors, so we'll swap out the 3416s for some more Jelly Bean like 2N2222s or 3904s or whatever. And we'll also flip some polarities and try some of these 4061s, which came from that same electronics lot. 4061s are the original part number that was in the Zonk machine too. So if all that sounds interesting to you, stick around. Right, so the 3416 here from Teledyne. Teledyne was a company started in like early 60s, I believe. They're really more like a company of companies. They're just one of those like companies that just bought up a whole bunch of other smaller companies. And I don't actually think they ever really made stuff of their own design. It was more just like their subsidiaries that made the stuff. But yeah, this was in a lot of those electronics parts I bought. And it is an NPN silicon, just like the 2N3416. You're probably wondering, well, this isn't 2N3416, this is T3416. And that's true. This was a common thing to do for like semiconductor manufacturers to change the prefix on the JEDEC part number. JEDEC is sort of the third-party consortium, I guess you could say, who maintains and regulates the electronics specs and components across different manufacturers and different disciplines. It was important, especially for the military context that they just came out of World War II, to have consistency across electronics parts so that you didn't end up putting some part that supposedly had the same specs in some other military equipment and helicopters start falling out of the sky. So the JEDEC is a organization that maintains these general part numbers, and then different semiconductor manufacturers can go and build stuff that meet those part number specs. So a 2N3416 isn't a part, it's almost just like a data sheet, and then different companies can make parts that match the specs on those data sheets or maybe exceeds them. So T3416, I am hypothesizing that that is in fact a 2N3416. It just has T for Teledyne as the manufacturer specific prefix. Different companies did the same thing, like Fairchild had the mu and then the letter A, so you'll see like 741 op amps, you'll see a mu A 741, that's Fairchild. LM 741 is Texas Instruments. You'll sometimes see, what's the Motorola MPS, I believe is Motorola parts, MPS, and then a part number. And then confusing, you'll see other companies selling under those prefixes to essentially try to meet the demand. I believe the point was to cause, like when you're doing repairs, to go and search out that specific part. You end up looking for a Teledyne 3416 rather than just a 3416. And hopefully it would drive more business back to Teledyne for replacement parts. That's my guess. It's just a marketing thing. Ultimately, if it was marketed as a 3416, it has to meet the specs that are listed on that data sheet. It is possible that T3416 is a house number that happens to line up with that JEDEC part number designation 2N3416, and it happens to also be an NPN silicon. I would hope they wouldn't do that to avoid the confusion we could be having right now. I'm fairly confident that this is in fact the 2N3416, just with the Teledyne T prefix. So this is the schematic for the Reeves Electro ZO that I drew up. It is, the pedal, like I said, it's based on the Zonk machine Mark II. The Zonk machine Mark I is definitely the more popular. Like when someone says, I have a Zonk machine, or I want to play a Zonk machine, or I like a Zonk machine, they're probably talking about Mark I, which is the 3-transistor germanium version. The Mark II is a 2-transistor silicon version. I think there were some interim ones that were like 3-transistor silicon that were called Mark IIs. But the point of the Mark II was to be a cheaper alternative. And so that's the Zoe. We'll look at the original Mark II. So first off, shout out to Philip Bryant for the schematic here. They drew this up, and it appears to be from 2003, it looks like the watermark is. And they are from this website, fuzzcentral.tripod.com. I think that redirects to a different website if you go to this. So if you're interested in seeing some more schematics, I think they have like DIY projects and schematics on their site, so go check them out. And thank you to Philip Bryant for the schematic. So as you can see, pretty simple circuit here, fairly reminiscent of a fuzz face. Pretty much any small part count 2 transistor fuzz is going to kind of look like a fuzz face. Major difference, of course, is the way that Q1 is getting bias. Instead of having a feedback resistor from the emitter of Q2 coming back to Q1, we have a biasing resistor coming off the collector of Q1 over here to the base of Q1. The input comes in straight into a 10 microfarad cap, then into the base of Q1. Q1 has its emitter grounded, and then the collector is being powered with a 47K up here to the power rail. Just like a fuzz face, the base of Q2 is DC coupled to the collector of Q1. We have a very similar fuzz control to a fuzz face with the 25 microfarad, 22, 25 microfarad bypass cap around the fuzz control, 10K collector resistor for Q2, and then 100 nanofarad cap out, a 2.2 meg series resistor, and a swell control setup here that's sort of set up backwards with the input signal coming into the wiper. For what I understand reading like forum posts, messing around with this here tends to get this pedal to work a lot better. It might have been a consequence of the specific transistors that John Hornby Skewes were building with at the time to need this 2.2 meg resistor. You'll see in a second that the Reeves changed that part out. It also says here that sometimes changing the bias up on the transistor is necessary. That'll depend on the specific traits of the transistors being used. You'll also notice here that the 9-volt battery, the negative terminal is what's connected to the power rail and the positive terminal is connected to the ground. The consequence of using PNP transistors is that you have to do negative or positive ground like this is shown here. Reeves switched that, so now using MPN transistors, the 2N3416, Reeves was able to use negative ground for a standard power hookup. Because of the nature of the way the Reeves pedals are built, which if you haven't seen them, go check them out. They're built in a style that's called point-to-point, sometimes called like dead bug. The components inside are laid out in a very specific way that has a sort of aesthetic quality. I'll talk about that a little bit more later, but because of the way the components are in there and sort of flying in that dead bug style, you can't have a 9-volt battery bouncing around inside the enclosure. And so all the Reeves pedals are powered with DC jack. And so doing PNP, it would be frustrating because you would have to make sure no one daisy chain pedal together. It would have to have its own power supply or its own isolated output from a power brick. Mark II Zonk machine here, though, used PNP transistors, 4061s, was powered by an internal battery in the enclosure, no DC jack. So it has its own power source. It doesn't have to worry about shorting out the power supply for negative versus positive ground. So this is the Zonk II, the original fuzz pedal. Here is a Reeves Electro Zoe. I did draw up this schematic just based off of pictures, so that's always going to be less accurate than having the pedal on hand. All the Reeves Electro pedals are really hard to get your hands on. He doesn't make that many of them, and he also doesn't do like a wait list. He just will make a batch of them and then release them out, and then they get bought up in seconds. So I've never been able to catch one. I would like to open one up for the channel, of course, but I've never been able to get my hands on one. And they also sell pretty quick used as well. They're also really expensive. They're like $400 to $500. But yeah, here is the Zoe. So obviously clear lineage between these two pedals. And he admits as such. It's not like he's trying to hide that it's a Zonk II. But it is modified in some ways. We have a 10 microfarad cap coming in. This cap is technically backwards. We'll talk about that a little bit later. The first thing it hits is a potentiometer. I believe he calls that his drift control. The way he describes it is like it's supposed to be mimicking like components going out of tolerance and drifting over time, hence the name of the control. However, it's set up just like a series resistance like you would see on other fuzz effects. The acid fuzz we looked at a couple weeks ago has this as a trim pot on the PCB or strip board. The Analog Man Sunface has this control in it. It basically just increases it cuts the signal going into the pedal and changes the impedance. As you turn it up, the pedal gets less gainy and more tame, I guess you could say. We still have the same 680K biasing resistor coming over to the base, still the 47K collector resistor for Q1, still DC coupled into the base of Q2. Emitter resistor for Q2 is now a fixed 3.3K with a 22 microfarad bypass cap. The collector resistor here is a 10K trim pot. There do appear to be two different versions of the Zoe. Some of them have this cap going from the collector to base. I'm not certain of the value here. I think 470 is a decent guess. That's usually, you want something usually around like 100 to 1 nanofarad, 100 picofarad to 1 nanofarad is the usual value for this spot. It looks like in some pictures I can see a 47. I'm not certain what the value of this cap is. If anybody by the way, if anybody has a ZO and wants to confirm some values, hit me up. graybenchelec@gmail.com. 10 nanofarad output cap, and then a little resistor divider here with a 220K to ground and a 220K in series with the output volume pot, which has been corrected from the original version, which was hooked up technically like backwards. 3416 are NPN transistors, like we said, so we use positive 9-volt power, standard negative ground. And then, like I said, I see two different versions, and there's differences between the two. So some of the ZOs, I think the newer one, you'll see this 10K control, which I don't recall what it's called. I'll put it up on the screen. And then I think the older ones, you see a switch, and that switch is controlling the emitter resistance here. The new ones, I believe, have the 3.3K fixed resistor. The older ones have a switch, something like this, where the bypass cap is always there, but it switches between a 4.7K fixed resistor and what I'm guessing is like a 10K trim pot. And there's a switch on top that switches between the two. For that other version, the 10K pot here gets switched out for just a fixed 10K resistor. And also on those versions, I don't see this capacitor connecting the collector to base. So that's one of the things we'll try is we'll pull this out when we look at it on the breadboard and see what that does. I can tell you right now it's going to roll off a bunch of high end. It's going to take out some of that harshness from the silicon transistors, but we'll play with that. So yeah, this is the Reeves Electro ZO, best as I could trace just looking at pictures. So now let's have a look at the breadboard and we'll do a listening test and we'll play with the circuit and see what happens. All right, so here is the Reeves Electro ZO mocked up on the breadboard here. So just going to go through the circuit quick. We have a orange wire here. This is the input from the input jack coming through the 10 microfarad capacitor right out to the capacitor, the first potentiometer here, the drift potentiometer. I forgot to say, I can't see the bottom of the potentiometer, so I don't know the values. So I guessed at those. 500K is the swell value from the original Zonk, so that's what I put in for the output volume here. Collector resistance, and whatever the heck the name of that control is, I used a linear 10K, and the input resistance, the drift control here, is a audio 50K. So we're coming out from the cap into that pot, back out into the base of Q1. This is going to be the slot for Q1 here when we put that in. That has the 680K coming over to the base, and then the 47K right there coming up to the power rail. Standard 9-volt power here, positive 9-volt that is. The collector here through the yellow wire is DC coupled straight to the base of Q2. That has the little capacitor here. This is the 470 picofarads in there now. Here is the bypass cap, the 22 microfarad. And here is the emitter resistance for Q2. I have it moved down here so it's easier to swap out. And right now it is the 3.3K. This is the standard value for the new ZO. Here is the 10 nanofarad output cap. I should mention that's one change for the ZO. The output cap for the original Zonk II was 100 nanofarad. On the ZO, it is a 10 nanofarad. So we got a 10 nanofarad cap there coming out of the collector of Q2, and here are the two 20Ks making that voltage divider, and then out from there to the volume pot, wiper out to the output through the white cable here to the output jack. So that is the ZO mocked up on the breadboard. For transistors, I pulled out 10 of the T3416 Teledyne transistors and just measured the gains. These are silicon transistors, so there shouldn't be any leakage. It should be in the pico amps, femto amps, really small. For the DCA75, it doesn't measure that far down, so effectively zero leakage. And these are just the gain, so this is just a ratio of collector current to base current. And we'll swap these around and see what gains work with what. For right now, I think since the circuit is fairly fuzz face looking, we'll just start with some typical fuzz face values. So we'll just take this 99 here, throw that into the circuit, and we'll take the 122 here and throw that in, and we'll see what happens. All right, so I got the ZO here on the breadboard hooked up for a listening test. The controls, I have the drift control here turned all the way down, so this should be like least amount of drift. I believe I lined up the pots correctly for that. We'll see. The bias control here, which is the collector of Q2. I don't know, I forget what this control is called, or what he calls it. I've got it just 12 o'clock, and then the volume is 12 o'clock. Amp is a modded Bassman. The mic is an SM57. The guitar is a Tele with a humbucker in the bridge. I might switch that to the split coil thing. And yeah, so let's hear the clean tone. So just a little bit of hair on it there, a little bit bright. Let's go ahead and kick in the pedal here. pretty gated there. Let's turn up the bias control. Okay, so that's a lot better. Bias control seems to have pretty limited sweep. It gets pretty gated pretty quick. That could be a consequence of the transistors we're using here. We'll play with those in a second. We'll leave the bias control where it is, about 2 o'clock or so. Let's go through the drift control and see what that sounds like. All right, so you can see there, we're adding that series resistance, so we're getting less signal into the fuzz pedal, which is bringing down the gain. Essentially, it's also getting brighter as the impedance increases. Let's essentially do the same thing, but I'll start just turning up my volume control, or turning down my volume on my guitar, and you'll be able to hear the same thing come through. It'll be similar. It does seem to darken a little more than a fuzz face would, in my experience. I'm not sure why that is. So we're at about a 4 right now. Fairly similar. It seems like up here on the somewhere around here, like 3 o'clock or so, all the way to full like 5 o'clock is where the drift starts to sound a lot like the guitar roll back to 10 or so, or 7 or 8. So that is the drift control. The bias control we kind of saw, that's a little bit touchy. The volume control is just volume out. So let's start messing with the components and see what happens. The first thing I'm going to try is going with a different HFE transistor. So we have about 99 in Q1 and a 122 in Q2. Let's try going even higher for Q2 and we'll see what happens. So that's the 122. And we'll go with one of these 186 HFE transistors, and we'll see what that sounds like, and if that messes with our bias control, how that works. All right, so still pretty gated beyond, earlier than 12 o'clock on the bias knob. Let's turn, I'm calling that bias. It has some other name that they call it, I just can't remember. So that's the higher HFE for Q2. Sounds pretty similar otherwise, I would say. Let's match it. Let's go a high HFE for Q1 as well. We'll pull out, that's the 99. Here's a 183 we can do for Q1. Throw that in there, we'll see what happens. All right, so immediately our bias knob has come to life. Now that we have more current driving into Q2, we have more gain. We're able to push and use more of the available gain and current that the bias knob was restricting previously with lower HFE Q1. So definitely for this build, I would go higher HFE than 99 for Q1. Right now we're at 183 and 186. And it feels like it's working more like Reeves Electro intended. All right, so I think we're going to stick with those values. So we're looking somewhere, I would say, as a general spec, like probably 150 to 200 for both transistors, probably is the way to go. Let's try switching some other stuff out. So throughout these tests, I've been feeling the pedal sounds kind of woofy. So my first thought is let's drop down that 10 microfarad input cap. So we're going to take this 10 microfarad cap and we're going to reduce that. I've got 3 other caps here. We're just going to start dropping down like orders of magnitude. So here's our 10 microfarad cap. Actually, first off, let's just try one quick thing. So you'll notice here we have a NPN circuit now, which means we have positive power coming through here, through the 47K, through the 680K to the base, which means technically there should be some positive voltage here. It's going to be low, probably less than a volt, but that's coming through to the 50K to the capacitor here, which means technically the positive side of the capacitor should be on the circuit side here. However, the Reeves was definitely wired with the other way, with the positive pointing to the guitar, essentially. So let's just flip that around and see if it sounds any different. I can tell you from experience, it's low enough voltage, it's not really going to be a risk to the capacitor itself. But let's see if sonically there's any detectable difference. We're getting more oscillations because we have more gain now. Let's pull back the drift control, maybe tame that a bit. So this is definitely a breadboard problem. Let's see. We got a lot of wires flying here, so that's not that crazy. All right, we're just gonna pull back the guitar volume a little bit to just eliminate. Still plenty fuzzy. So let's just flip this capacitor and see what happens. Yeah, so no discernible difference there. We'll switch that back to the way Reeves had it. So let's try dropping that down. So this is a 10 microfarad. Let's put in a 1 microfarad. So order of magnitude smaller. See what happens. So a little bit less woofy there. Let's try a 100, without dropping the capacitor, let's try a 100 nanofarad cap. Oh, there you go. All right, let's try that. Well, the oscillations went away. That's one benefit. A lot of that low frequency content's gone now because we have that smaller output cap and we're changing the roll off for that high pass filter. Yeah, so high gain circuits, very sensitive. All right, so that's even more base cut. It might be a little bit too much, but I do kind of like the 100 nanofarad there too. Try the 10 nanofarad. This is probably gonna be too thin here. Yeah, so I would say that's too thin. So I like 100 nanofarad. I also like 1 microfarad. The 10 feels a little woofy to me. So let's try messing with the emitter resistor for Q2. There are 2 versions of the ZO, at least that I've seen, and the earlier version, I believe, uses a switch between a 4.7K and what I'm guessing is a 10K trim pot. This version, this was the more recent version that had the 3.3K fixed resistor. So let's pull that out and we'll put in the 4.7K and we'll see what that sounds like. All right, so a little change to the fuzz sound there. In this earlier version, the bias pot is gone and that switch replaces it physically in the enclosure. And it's just replaced with a fixed 10K collector resistor. So let me switch that out. So we'll take out that pot. We'll just move this over here. And we'll put in that 10K.
This 10K. Yeah, 10K resistor. And this is from the collector up to the power rail. Oops. So this is closer to the way the earlier Zoe is set up. So you'll note this doesn't do anything now because it's out of circuit. I'm rolling back my guitar volume because it oscillates when it's at full volume. All right, so that's out. Let's go back to the standard setup for the newer Zoe. At least there's two versions. I believe the one with the 3.3K and the adjustable bias. I believe that's the newer version. So let's go back to that setup. So that's 10K out, pot back into the collector, 4.7K emitter resistance out, and 3.3K back in. Let's make sure that's still making noise. Okay, that's good. And let's try just pulling out the little capacitor here, see what that does. Yeah, so you can see there's a lot of high-end crap there that is not being removed by this capacitor, so. Okay, that's pretty ugly right there. Put that back in. Thank you very much. So again, that might be one of those things that's exacerbated by the breadboard and all these flying wires here, but. All right, so I got some 2N22 NPN transistors. The 2N22 is a pretty standard part. You can find these anywhere. These happen to be Motorola's, but it's a pretty standard part number. We're gonna pull out the 3416s here and pop these in. The gains on these were like 175 each, so slightly lower than the 3416s, but shouldn't be enough to really make a difference. And of course, these are in the TO18 package versus the TO92 package. The 3416s that Reeves uses is an older package that I don't know the number for. I don't know the make of theirs either, maybe General Electric. All right, let's see what happens here. Same oscillation at max guitar volume, so I'm gonna keep rolling that back a bit. so hopefully you can hear, not a huge difference there. Two silicon transistors with the roughly pretty close to the same HFE are going to sound pretty much the same in the same circuit. I'm going to try switching the polarity of the power and a couple of the components, and then we'll try the 4061s. All right, so now I've switched over to the 4061 PMP transistors. Power switched over to -9 volts for the power rail. The bypass cap is turned around, and I turned around the input cap as well, which is still incorrect for the circuit that's here, but is backwards like the Reeves. It's getting a bit confusing now, but we have 4061s. Side note, 4061s have a weird pinout. It's emitter collector base if you're looking at the face of the transistor. So I've had to sort of twist the leads to make that work. Otherwise, I haven't changed anything. The gains on these are both 188 or so almost exactly the same as the 3416s, just PMP. I'm going to switch the input cap over to make it correct for the Zonk II. Actually, you know what? I was wrong. This is now the way it was before. Let's go back to that. This is with the negative pointing towards the circuit for PMP. So this is correct to the Zonk II, not the Reeves. Let's switch that so it's the way the Reeves is, which is technically backwards. Same thing as the NPN, I don't think it makes a difference. It's such a low DC voltage, I don't think it matters. I don't think it's gonna be a risk to the cap, and it doesn't seem to make a difference sonically either. Not that I can hear. Let's change out the 3.3K emitter resistor here for a 4.7K. See what that does. All right, so that sounded really woofy now. I'm gonna switch out that 10 microfarad input cap for the 100 nanofarad. Let's see what that does. All right, that sounded better. Let's just play with the drift, see what that does. Okay, so it works more or less the same. We have less gain with the PMP, which I'm not quite sure why. Less gain with the PMP setup here. Let's go back to 33K emitter resistor. All right, I'm gonna roll back the guitar volume. We'll have a listen to what that sounds like. So the change relative to the guitar volume is more drastic with the PMP setup here. It rolls off much more quickly than the NPN version. right, so I hope some of you found that interesting or enjoyable, entertaining, whatever. If you did, I appreciate you hitting the like button and subscribing. When we come back next time, I'm going to try building one of these Zoe in the style that Reeves Electro builds their pedals. I know for a fact I'm not going to make it look as pretty as they do because they have a lot of experience doing that. But we'll try that point-to-point or dead bug style. We'll go with the standard setup that they have for their pedal, and we'll see how it sounds. I hope you'll come back and join me for that. I'm Joe from Graybench Electronics. Thank you for watching.